Hello, this is mathjazz from Almost Cool. I have today a bunch of assorted derivative problems. I am currently recording this in an airport and there's a lot of noise, but I will re-record this later for better sound. I just needed to get something up for my students who specifically asked for these 10 problems to be solved. So, uh, these problems come from the James... These problems are from the James Stewart Calculus book. They're being used under fair use and for educational purposes. Please support the author by purchasing his book if you're going to find these problems somehow and do them. But without any further ado, here is problem 1. We're going to find the derivative of cosine of x using the definition of derivative. So first we have to recall, of course, what the definition of derivative is. Here it is on the screen. Now, our function is cosine, so we're going to replace f in the definition with cosine, like so. And now we have to figure out what the value of this limit is. So the first thing we do is we're going to use the angle sum formula for cosine to split up cosine of x plus h into cosine of x times cosine of h minus sine of x sine of h. So, doing that, we're able to gather all of the cosine terms together into their own fraction, and all of the sine terms into their own fraction. Cosine of x and sine of x do not have h's in it, therefore they are constants relative to the limit, so they can be factored out of the limit. And now we recognize two limits that we should have memorized. The limit as h goes to 0 of cosine of h minus 1 over h, and the limit as h goes to 0 of sine of h over h. The first of these equals 0, and the second of these equals 1, so plugging those into the statement we have, we get cosine x times 0 minus sine x times 1, which is negative sine of x. And that proves the derivative of cosine of x. Here is problem 2. Suppose that the position of a particle was given by p of t equals 8 sine of t. Part A is find the velocity function, and part B is find the position and the velocity at time t equals 2 pi over 3. So, the velocity is just the derivative of position, so we take the derivative of 8 sine of t with respect to t, and we get we should get positive 8 cosine t. There is a typo on that slide, and I apologize. Plugging t equals 2 pi thirds into p and v gives us, well, p of 2 pi thirds is going to be sine of 2 pi thirds, and sine of 2 pi thirds is just going to be sine of pi thirds because of how our reference angles work. So again, there's a negative sign here, and I apologize for that. So sine of 2 pi thirds should be 8 times a half, which is equal to 4. Velocity is obtained the same way. We plug in 2 pi over 3 into cosine of 2 pi over 3. Hey, I have the sign correct on this slide. I apologize for the previous one. Which is going to be 8 times square root of 3 over 2, which is going to be positive 4 times square root of 3. Sorry, I kind of rushed these slides, but I'll have them fixed pretty soon. Problem 3. Suppose that f and g are defined as in the table, that h of t equals f of g of t, capital H of t equals g of f of t. Find h prime of 1 and capital H prime of 1. Well, this is just using the chain rule. So, using the chain rule, we get h prime of t equals f prime of t, g of t, times g prime of t. And similarly for capital H of t. And now we just plug in 1 into each of these. So, h prime of 1 is f of g of 1 times g prime of 1, which is f prime of 2 times 6, which is 5 times 6, which is 30, from the chart on the previous page. I'll show that on the screen for a bit. Maybe you can pause the video and write it down, because I will be rushing through h prime of t, or capital H prime of t, pretty soon. So, back to the problem. So, same thing with h prime of 1. We plug 1 into g prime of f of 1 times f prime of 1, and I claim, get 36 when we evaluate everything. Problem 4. Prove the quotient rule using the product rule and the chain rule. So, first we'll write up the quotient rule. What we'd like to do is use the product rule and the chain rule on the left-hand side and have the formula we get end up being the right-hand side, using only the product rule and the chain rule. No quotient rule. So doing that, first we're going to rewrite the left-hand side as a product instead of a quotient. Notice the -1 in the exponent. Then, using the product rule, we can split this apart like so. Just first function's derivative times the second function, plus the first function times the derivative of the second function. And we have a chain rule. The inside function is g of x. The outside function is the inverse function. And so, using the chain rule, we get f prime x times g of x to the -1 minus f of x times g of x to the -2 times g prime of x. And we rewrite these as fractions, like so. And we multiply by g over g on the first fraction, so we can combine fractions. And we end up getting the quotient rule that we all know and probably don't love. Anyway, problem number 5. So, we want to find the second derivative of y for this equation, x squared plus 4y squared equals 4. First, we have to find the first derivative. So we do that. So we just take the derivative of all the terms. Since the 4y squared term involves us taking the derivative of y, we have to multiply by dy dx as per the chain rule. And if you still haven't thought hard about why implicit differentiation is just the chain rule, I implore you to spend some time meditating on that. Anyway, the next thing we do is we solve for dy dx. We don't really have to. We can just take the derivative of 2x plus 8y times dy dx and then solve for d squared y dx squared, but I find it's easier to solve for dy dx, so I do it here. We have this. We're going to now take the derivative of dy dx by using the quotient rule, like so. So the derivative of the denominator times the numerator, I guess I switched that. The denominator times the derivative of the numerator. There we go. Minus the numerator times the derivative of the denominator is going to give us 4y minus 4x dy dx. And then we divide by the square of the denominator, which is 16x squared. There's a negative sign out in front because there was a negative sign out in front for dy dx. So now that we have this, we can actually plug our dy dx equation into our d squared y dx squared equation to get this and simplify. And if we really wanted to, we could go to our original equation, that ellipse. Let me show it to you. This ellipse, x squared plus 4y squared equals 4, we could solve that for y and plug that into this equation if we really wanted to, but I don't want to, so we won't do it. Okay, so this gives us d squared y dx squared, or the second derivative of y for that implicit function that we had. Here is problem 6. We want to find h prime of t when h of t equals arc cosine of t plus arc cotangent of t plus arc cotangent of 1 over t. We use the chain rule for this. We have to first remember what the derivative of arc cotangent is, or if we don't remember what it is, we have to prove it ourselves. Well, so I'll assume that you can remember this. Here's the arc cotangent's derivative. Now, using the chain rule, we're going to get that the derivative is equal to -1 over t squared plus 1. plus, that should be negative 1 over 1 over t squared plus 1 times negative 1 over t squared. And multiplying the two fractions together, we get negative 1 over t squared plus 1. We should have a plus here because we forgot to have a minus sign here. So this would have been a minus sign canceling with this minus sign. Can't seem to select it. It's the negative 1 over t squared. The highlighted plus sign should have been a minus sign, and it should have canceled, leaving a plus sign between the two fractions on the bottom line. That means that these two terms will add up to 0. Oh, that's kind of fun, that these two trig functions add together to have 0 as their derivative, which means that the two of them are constant. Sorry, the sum of them is constant. Kind of like how sine squared plus cosine squared is 1. Oh. Okay, so now we want to find the derivative of the square root of x to the x power. So to do this, we're going to have to use logarithmic differentiation because we have a variable in the denominator and a variable in the exponent. So we let y equal the desired function, and we take the natural log of both sides and simplify. And so that gives us x over 2 natural log of x equals ln of y. We take the derivative of both sides using the product rule on the right side. That gives us y prime over y equals 1/2 natural log of x plus 1/2. We multiply both sides by y, getting y prime equals the quantity 1/2 natural log of x plus 1/2 times the square root of x to the x power. It's not so bad. We're going to do it again with problem 8, where now we have cosine of x to the x power, and we're taking its derivative. So, same thing. We let y equal cosine of x to the x. We take the natural log of both sides and simplify. We use the product rule to take the derivative on the right side, and of course the derivative of ln y is y prime over y on the left side. So, once we have that, we multiply both sides by y, getting y prime equals the quantity natural log of cosine of x minus tangent of x times cosine of x to the x power. Okay, so let's go to problem 9. 9 is a fun one. We have to find a formula for the nth derivative of f if f is the natural log of x minus 1. Now doing this, first we're going to have to look at a few derivatives to get an idea of the pattern that's happening here. So we take 3 derivatives. I guess that's actually 4 derivatives. This is the third derivative, and this is the fourth on the bottom line. Okay, so looking at these derivatives, we try and get an idea for the pattern, and I'll let you think about it for a while. Pause the video. Okay, now that you're done pausing the video, what looks to me is that every derivative I take switches the sign of the derivative. The power of the denominator goes up by 1, and the numerator gets multiplied by the exponent in the denominator. So going from the second to the third derivative means multiplying by 2 in the numerator. So here's a formula that should do that. The nth derivative of f of x equals negative 1 to the n minus 1 power times n minus 1 factorial divided by x minus 1 to the n. Now, we have to first check to see if this works on the first derivative. So we plug in 1 for n, and it looks like it works. Notice that negative 1 to the 0 power is 1, that 1 minus 1 is 0, 0 factorial is 1, 1 times 1 is 1, so we got the numerator right. And then x minus 1 to the first power is x minus 1. So this does in fact look like the first derivative. The next thing we're going to do is we're going to see that, okay, if this function, or if this formula gives us the k minus 1 derivative, that is, if it works for some derivative. And we'll call that derivative the k minus 1 derivative. Like, for example, if it works for the third derivative, we'll just call that the 4 minus 1 derivative, okay? If this formula works, does it work for the k derivative, the one after it? If it works for a derivative, does this function work for the derivative after it? So, let's see. Well, if it works, that means that if we take the derivative of the formula, we should get the formula with one more number plugged into it. So what I mean by that is, for example, if it works for 3, and we take the derivative of the formula, and what we get is the derivative of 4, then we know the formula works. So we're going to do that. We have the k minus 1 derivative here, and we're taking the derivative of it. That's the first line. And using the power rule, notice the numerator is just a constant with respect to x, so that just factors out. The bottom is x minus 1 to some power, so that's just a power rule, a chain rule combination there. When we take this derivative, we get negative 1 to the k minus 1, because we gained a negative power because we're multiplying by, or because the power rule, we bring down the power in front, and since this is a negative power, we're getting another negative 1 in the numerator. Since the power was k minus 1, we're multiplying by k minus 1, which improves or increases our k minus 2 factorial to a k minus 1 factorial. And the power goes down by 1, so k minus 1 is a negative number, and going down from it gives us k. So using the power rule and the chain rule, we see that the derivative of our k minus 1 formula is this, negative 1 to the k minus 1 times k minus 1 factorial over x minus 1 to the k. And now we check, is this the formula when we plug k into the formula? And it in fact is. So what that means is that if this formula works for any derivative, it works for the derivative after that one. And since we know this works for the first derivative, we know that this works for all derivatives, because since it works for the first, it works for the second. But since it works for the second, it works for the third. Since it works for the third, it works for the fourth, and so on. So this technique is called mathematical induction. It's a powerful technique that allows mathematicians to prove an infinite collection of facts, so long as you can put them in an order and show that each fact being true makes the next fact true. And so again, we used mathematical induction to prove that this formula works for every natural number, which is an infinite number of numbers. Here's problem 10. The blue function we're going to call f, and the yellow function we'll call g. We're going to let u be f of g, v be g of f, and w be g of g. And we're going to find u prime of 1, v prime of 1, and w prime of 1. Okay, so let's get to that. We're going to use the chain rule. We look at the graph. We figure out the values of g of 1, g prime of 1, and f of 3. Why f of 3? Well, it's f prime. Sorry. That is an error. It should be f prime of 3. F prime of g of 1. G of 1 is 3, so we get f prime of 3. So let's see, what is f prime of 3? That's negative 1/4. We're going down 1 over 4. Okay, so f of 3 should be negative 1/4, not 15/4. Which means that when we plug these into our formula, we get negative 1/4 times negative 3, and we get positive 3/4. And we'll fix the slide in the next, in the remake of this video. So let's do v prime. V prime of 1 equals g prime of f of 1 times f prime of 1. We have to find f of 1 f prime of 1 and g prime of 2. So let's take a look. Well, f of 1 is 2, f prime of 1 is also 2, and g prime of 2 should be negative 3. Not g of 2, but g prime of 2 is negative 3. No, g prime of 2 doesn't exist. Notice there's a sharp corner at 2. So what we get here is something that doesn't exist times 2, which doesn't exist. So this is wrong, but I have to show it to get onto the next slide. So v prime doesn't exist because g prime of 2 doesn't exist, and g prime of 2 doesn't exist because g has a sharp corner at x equals 2. Okay, now w prime of 1. We're going to find g prime of g of 1 times g prime of 1. So g of 1 is 3, g prime of 1 is negative 3, and we need to find g prime of 3, which is in fact 2/3. So our answer here will be, it just happens that g of 3 and g prime of 3 both equal 2/3. I lucked out here, but that is a typo. I should look for g prime of 3, not g of 3. Anyway, so we get g prime of 3 is 2/3 times g of prime of 1, which is negative 3, and we get negative 2 as our answer. Thank you for watching this video. Contact information is on the screen. Please email your questions to me and I will answer them. Also, I hope that you're enjoying learning calculus. Have a great day. Goodbye.